In this video, we're going to be going over the moment of inertia. By definition, the moment of inertia about the x-axis is going to be the integral of y squared dA, and about the y-axis, the integral of x squared dA. Now, I like to think of the moment of inertia as a shape's tendency to want to bend. It's based off of how much area is far away from that section's own centroid. So the more area you have sitting away from the centroid, the higher the moment of inertia is going to be. And the closer all the area is to the centroid, the lower the moment of inertia is going to be. And so these have all been calculated for common shapes. And they're usually tabulated in the back of your textbook, or you can just look them up online. But we'll just go over a few right now. So if you have a rectangle, and this is its centroid, that's the x-axis, that's the y-axis. Your moment of inertia is going to be equal to bh cubed over 12. Now, there's a couple different ways you can think about this. You can always think of this as being your base and this as your height. In that case, this is going to be ix, and then iy is going to be hb cubed over 12. But the way I like to think about it is to just remember this equation right here. So you only have to remember one equation, and then you just have to remember that b is going to be the dimension parallel to the axis you're taking your moment of inertia about. So if you wanted to find ix, again, centroid's there, that's y, this is x. This is going to be your b dimension. And then by default, obviously, this will be your h dimension. But if you want to find iy, this is your section, this is a centroid, that's y, that's x. So again, b is the dimension parallel to the axis in question. So for our y-axis, parallel to our y-axis is this dimension here. And so then I define that as b. And then, of course, by default, that's going to be h. It doesn't matter how you remember it. I feel like it's easier for me to just have to remember one equation and then just remember that b is always going to be parallel to whichever axis you're looking at. That's easier for me. It might be easier for you to just remember ix is bh cubed over 12 and iy is hb cubed over 12. And this is always b, and this is always h. But that can get confusing if your axes change for whatever reason. This ends up being y, and this ends up being x. Then you may not remember what equation is which. So that's why I like to remember it this way. So again, just remember B is always going to be your dimension parallel to your axis that you're taking your moment of inertia about, and you'll be all right. All right. So that's for a rectangle. If we look at a triangle, here's the centroid, your y-axis, your x-axis. Your moment of inertia of a triangle is going to be BH cubed over 36. And again, that's always your dimension parallel to the axis you're taking your moment of inertia about. And then lastly, we'll look at a circle where that's y and that's x. And of course, this is going to have a radius of r. Your I is going to equal pi r to the fourth all over 4. Now, one thing to note and to recognize is that all of these moment of inertias are about axes set at the centroid of each of these shapes. So if we had a shape, let's say, we know the equation for moment of inertia if it's taken about this x-axis, but what if we want it taken about this x-axis right there? So this is our current axis, and this is our new axis. We want the moment of inertia now taken about this axis right here. There's a thing called the parallel axis theorem. And this allows us to change the location of the axis that we're taking our moment of inertia about. So, like I said, if we have this rectangle, so this here is our current axis, and we want to know the moment of inertia about this new axis here. The equation used for the parallel axis theorem is going to be Ix equals Ix prime plus AD squared, where this is the moment of inertia about your new axis. This is the moment inertia about the current axis. This is the area of your section or your shape. And then this here, that D, is going to be your distance between the current and new axis. So visually, it's going to be this distance here. So if we just run through an example of the parallel axis theorem really fast, just so you can see that in action, let's take this rectangle. Let's say it has a height of 2, width of 6. We'll just say they're inches, give it some units. And we want to know the moment of inertia about, let's just say this axis right here. So where it lines up there. All right, we want this to be our new axis. So the first thing that we're going to do is find the moment of inertia about the current axis. So we know the Ix about its own centroid. So here is going to be, just from this table up here, we know that it's this equation right there. So Ix prime going to equal bh cubed over 12. And in this case, b is going to be the dimension parallel to x. So x is here, parallel, so that's going to be 6 inches. Times h is the other dimension, so 2 inches cubed all over 12. Plug that into your calculator. And you'll get 4 inches to the 4th. So now we've got this part of the equation. Now we just need this part of the equation. So we can say that Ix is going to equal Ix prime plus AD squared. So that's going to be equal to 4 inches to the 4th, plus area of this section is just base times height, so 6 inches times 2 inches. And then D is going to be that distance between the current and the new axis. So that's there, and D is going to equal 2 inches divided by 2, which is going to be 1 inch. So it's 1 inch squared. Plug that into your calculator, and you're going to get 4 plus 12 equals 16 inches to the 4th. And that's your new moment of inertia about its new axis. And you can see that as more area moves away from the axis in question, your moment of inertia gets higher. So for this axis, it's higher than if it was this axis, which logically makes sense, so we did this correctly. So sometimes you'll be asked to evaluate moment of inertia of a shaded region where this has some equation associated with it. Let's say y equals x cubed. So that's when you're going to use those by definition equations. Which we talked about above. And the way you're going to do that is you're going to set it up similarly to how we found centroids. So you're going to take just a little cut here, and you're going to find the area of that little section and then sum them together. So this distance here is going to be y. This is going to be dx, and so of course dA is going to equal just base times height, so y dx, and then we know that y equals x cubed, so you can plug x cubed in right there. So dA really equals x cubed dx, and then you can just plug that into either that equation or that equation, depending on which one you're trying to find, and then you can just simply solve for your moment of inertia. Now, sometimes you will be given weird-looking shapes like that, and it says, find the moment of inertia about that x-axis. The thing you're going to want to do is you're going to want to break this down into those familiar shapes that we know equations for. And so we can say, okay, this is going to be shape 1, 2, 3, 4, and 5. So break down into common shapes. Again, all these shapes we know the equations for. And then you can find Ix prime for each shape. And then once you have all your Ix primes, you can go ahead and find Ix for each shape. And you're going to do that by using the parallel axis theorem. Which was shown above. And we went through an example of that as well. And then you're just going to take a sum of all your individual Ix for each shape, and that's going to equal your total Ix. And it's as simple as that. That's how you're going to find your moment of inertia. So, written examples of both of these situations can be found right above this video, and those go through step by step how to do that. If you have additional questions, though, head over to our homework help page. Or if you want to sit down and talk through it, head over to our tutoring page and you can set up an appointment where we can talk through this a little bit more.